Okay, good. Let's take out the worksheet called Proving that a Sequence Has a Limit. How'd it go? If you completely understood what we did last week, then why didn't you do it? Snow day, forgot. Okay, so good. So we want to do the limit as n goes to infinity of 1 over cube root n minus 2. And this is negative 2. Okay, so sorry for anyone watching. What's up?
It's like super unfocused. Okay, there we go.
No, it just doesn't. It doesn't like white. It doesn't like the whiteboard.
Yeah, I can tell that. Yeah.
Good. Anyone watching at home? Hopefully you can hear me. We need to prove that this limit is negative 2, which it appears to be. So we can make a picture to try to understand this better. And the picture is going to look something like this. When I plug in 1, what do I get?
Negative 1.
Negative 1. And if I plug in 2, what do I get? Oh, gross. I refuse to plug in 2. Let's plug in something else. 8. Much better idea. So if I plug in 8, then I get 1 minus 2, so like negative 1.5, right? So, okay. So already I'm feeling this. What I'm feeling is that this is going to get closer and closer to negative 2, but slowly. More slowly than the one that we did last class, yeah?
Yeah.
Okay, so what is it that I really need to prove? What I need to prove is that for any possible epsilon greater than 0, and epsilon is the challenge, I don't know why I did that, epsilon is the challenge that is issued by someone who is skeptical, and this is negative 2 plus epsilon, this is negative 2 minus epsilon. For any possible epsilon, I can go out far enough such to some point n, so there exists an n greater than 0, such that if I go out to that point n, then everything past that has the property that that nth term is between negative 2 minus epsilon and negative 2 plus epsilon. Alright, so before we actually get started, can we kind of just do a little bit of like pre-think about this? I mentioned that I had to go all the way out to 8 in order to get like half closer from where I started. So maybe we should just like try a couple. Like what if someone challenged me with an epsilon of 1 over 1,000, no, 1 over 10. Someone challenged me with an epsilon of 1 over 10.
I challenge you.
How far out do I have to go?
1,000.
Yeah, now it's like 1,000, right? Because only when I go all the way up to like 1,000 will it be the what's the temperature?
I'm gonna send a work order in and put it into.
Yeah, there's just no heat, right? Basically.
Yeah, it's like 65.
Yeah.
It's supposed to be 7, so it's all 5 degrees. So we're gonna. I'll send a work order in.
Okay, thank you.
I had to, readjust this or replace you.
5 degrees.
Okay.
All right.
Good luck. Okay.
Well, I'm gonna send it in.
Okay.
Yeah.
Okay. Good. Okay. So yeah, if I want to get within 1/10, then I just feel that I have to go out to 1,000 before the cube root of 1,000 will be 10. So that's gonna work. So okay. So yeah. So my answer is that n is like 1,000. And I guess I can do another one. Like what if I wanna be within 100th? How far out do I have to go?
10,000.
Yeah, 100 cubed, which is like a million. Yeah, so it seems I'm gonna have to go out to like 1,000,000. All right, so already, shall we conjecture how far out we have to go? How far out do we have to go? Probably. Given an arbitrary epsilon.
1 over epsilon.
1 over epsilon cubed. Okay, so I'm pretty sure that that's correct. already, so that's good to like do that maybe in advance. But anyway, the algebra is gonna reveal the answer anyway. Okay, so this task comes in two parts. Part one is to discover what this relationship is. And we kind of think that we have already discovered it actually, probably. So hopefully we'll get the same thing when we do the algebra. Okay, well to discover the relationship, let's find the, let's start with the thing I'm trying to prove. And the thing I'm trying to prove is that the nth term is between -2 minus epsilon and -2 plus epsilon. Okay, so that means that this is 1 over cube root n minus 2, and this is -2 plus epsilon. Okay, so I'm going to now try to work backwards to discover which n's make this true. Okay, well I can immediately get rid of some -2's, so that gives me this. Okay, now what should we do? Yeah.
Use absolute values.
Yeah, I could use absolute values, or I could just kind of use just non-absolute values and just be like, that's true, but like I kind of don't care about that right now. What I really care about is like this.
Doesn't it always return a positive value?
Because this is always positive, so telling me that this positive thing is bigger than negative epsilon is like kind of useless information, I guess. Okay, now we can do 2 more algebra moves. We can reciprocate, flipping the sign. So this means that cube root n is greater than 1 over epsilon. And finally, cube both sides, which is legitimate as long as everything is positive, which it is. So n is bigger than 1 over epsilon cubed. Okay, so indeed, doing the algebra got me to the same place that common sense got me. But all I have really done is I have discovered the algebraic relationship that holds between the challenge and the response. Armed with that knowledge, I can now do the actual proof. Okay, so the actual proof, are you rotating if necessary? The actual proof says I need to take any possible challenge and then respond. So okay, so we're going to take an arbitrary epsilon greater than 0, and we are going to respond to that person. How do we respond? Well, that's what we just discovered, right? We discovered that this is how far out I have to go in order to make my thing true. So I'm going to set n to be 1 over epsilon cubed. And now I think it's all going to work. And what do I mean by it's all going to work? Well, what I need to show is, the claim that I'm making, is that if I go out past this number, big N, then the thing that I want to be true will be true. Okay? So how do I show that this conditional is true? Well, the way to prove a conditional is to assume the antecedent and derive the consequent. So let's assume, or you can write suppose, or you gotta write something though, that I have gone out past this special place. Well, by definition, n is 1 over epsilon cubed, so we know that n is bigger than 1 over epsilon cubed. And from this, I need to show that the nth term is between -2 minus epsilon and -2 plus epsilon. But I have my discovery phase as a guide for sort of what to do next, because it's basically just the reverse steps. So I can cube root both sides, so this tells me that cube root n is greater than 1 over epsilon. I can reciprocate both sides, so 1 over cube root n is less than epsilon. Okay, and now there's like a kind of an awkward moment, it's like slightly awkward, in which I do, in order for it to be part of the technical definition, I do need to show that it's between. So how do I get that it's between negative epsilon and epsilon? Yeah.
Well, you do a reverse absolute value.
Yeah, or not. You could do that, or not. Or you could just say like, dude, here's like a math fact for you. Like, any positive number is bigger than any negative number, and therefore by placing those two inequalities side by side by the definition of compound inequality, then this holds. Or you could do some kind of thing with absolute values, whichever one you're more comfortable with. Okay, and now final step is subtract 2. And so we showed exactly what we wanted to show. That the nth term is between -2 minus epsilon and -2 plus epsilon. Cool. Okay, and then that just completes the proof. All right, how you guys feel about this? Good. All right. You're gonna do the back for homework. All right. Let's learn 2 new things. Fun new thing number 1.
Your job.
Yeah. Good. All right. So. Can you use a new black marker? No, other one. Yeah. Thanks. Okay. Check it out. There are these very useful formulas. One of them we have seen already, and that is that if you add up 1 plus 2 plus 3 all the way up to n, this is n plus 1 over 2. Okay, and we proved this. I'll put prove in quotes because we kind of had a lot of like dots floating around in the middle of our group. More on that later. So I'll say we discovered that this was true. Whether we proved it or not, maybe is a matter of opinion. All right, I want to discover some more facts. I would like to know what the sum of the squares are. In other words, 1 plus 4 plus 9 plus all the way up to n squared. All right, there is also a cute little beautiful formula for this, but it's more difficult to do, and actually we'll talk about some other ways you could have come up with this in the past. All right, there's a couple different ways. I mean, there's basically one way to do this. It's just a matter of how much you want to understand the method first. I don't know, what do you guys want, a little understanding or a lot?
A lot. A little.
Good good question. Okay, so here we go. Let y be, okay, take a, this is a fact. Take a linear equation. You guys did this last year. Linear equations have certain nice properties. So like, just go like 1, 2, 3, 4, 5 or whatever.
First and second differences.
Yeah, so like if you plug in 1, you just get like
8.
8, I guess. If you plug in 2, 11. Yeah, like, no, not 13.
11.
11. Yeah, good job, guys. And then like 14,
17.
and then like 17, like 20. Okay, so, I'm just like adding 3 each time, because that's kind of like what linear functions do. All right, good. Not so impressed. Quadratics have a more exciting pattern. And, okay, let's just go like 1, 2, 3, 4, 5 or whatever. And, yeah, we see that this is like 1, 4, 9, 16, 25. Is there any kind of pattern here?
Yes.
There is, yeah. So if I, so if I look at the differences between successive numbers, then I get plus 3, plus 5, plus 7, plus 9. And this 3, 5, 7, 9 thing looks very familiar. That pattern is going up by 2 every time. And so I strongly feel that this is like a linear relationship, this 3, 5, 7, 9. And of course it is, because you can even, if you're like skeptical or something, you can even take differences and see that those differences are 2. Yeah? Rashid also, can you raise the board? Okay, well, next step. Do y equals x cubed. What are we going to find here? Let's do 1, 2, 3, 4, 5, 6. Okay, do you all know your perfect cubes? Of course you do.
27.
64, 125.
Yeah.
And then
216.
Ooh, good. We are ready for elementary school math team. Alright, right. So let's look at the pattern here. And okay, here I'm going up by 7, up by 19, 20, 37. Back me up on this graph. 61 and something. 91?
Yeah.
Good. Okay. Anyone recognize these numbers as being part of any well-known pattern?
Yeah.
Bunch of liars. No, not, no,
Yeah,
bunch
very
of liars.
good.
I'm not really sure what that is.
The difference about
But do you have a conjecture?
Then we
It's a
can take the
third.
difference twice more, 2 more times, and then it'll be
But if we take the differences, then it will be a one.
Okay, good.
I'm
Yeah,
guessing
so
it's
perhaps
fine.
we could examine these numbers to see if they like have some kind of pattern to them by looking at their differences. And I get 12, something, 18, 24, and 30. Oh, damn, now I see what's going on. 12, 18, 24, 30, that's like a linear relationship for sure, right?
Yeah.
Yeah, and so, well, if that's linear, then what I just learned in the previous problem is that a quadratic function grows at like a linear rate, right? In other words, the gap between numbers from a quadratic function are linear. So if this is linear, then this must be, and I'm being kind of vague here, some quadratic, okay? Those numbers, 7, 19, 37, 61, 91, must be some quadratic. Because it's quadratics which grow at a linear rate. Cool? Okay. Well, and what I'm about to do right now is kind of like how calculus got invented, but I won't explain. You can think of this 7 as being just 8 minus 1. And you can think of this 19 as being just 27 minus 8. And you can think of the 37 as being 64 minus 27. And so what's really going on here is if I add up all these numbers, if I add these up, 7, 19, 37, 61, 91, I can think of what I'm doing as adding up 216 minus 125, in other words, 6 cubed minus 5 cubed, plus, that's what 91 is, right? And then what is 61? Well, 61 is 125 minus 64. In other words, 5 cubed minus 4 cubed, yeah? So if this is 5 cubed minus 4 cubed, then this is 6 cubed minus 5 cubed. Okay, and then what's next?
64 minus 27.
Yeah, that's 64 minus 27. In other words, 4 cubed minus 3 cubed. And, okay, this is getting boring now. 27 minus 8 plus 8 minus 1. And you could even go all the way out to 1 minus 0. And this is 3 cubed minus 2 cubed. And 2 cubed minus 3
cubed, you're
squared.
writing 3 squared.
That's a mistake.
Right, there's also 3 squared before, yeah.
Okay, good. And this is 1 cubed minus 0 cubed. Okay, what is so? Of course, hopefully you're seeing this and hopefully I'm in frame. What is the conclusion? What is 6 cubed minus 5 cubed plus 5 cubed minus 4 cubed plus 4 cubed minus 3 cubed, etc., etc., etc.?
6 cubed.
It's just 6 cubed, right? Minus 0 cubed. In other words, if you add up a bunch of things, there's a name for this. We say that this telescopes. And that's because there's a long list of things, but they all just like collapse, like an old-timey like pirate telescope thingy. That's like, who knows what I'm talking about.
Yeah,
Or it's like you just like, they look like spike eyes.
Yeah, and you just go in and you just go. Okay, good. What's the point of all this? The point of all of this is that if I want to add up, like 91 and 61 and 37 and 19 and 7 and let's say 1 also, then what I'm gonna get is like sum of a quadratic. I'm not sure which quadratic, but there's gonna be some quadratic, it's gonna be the sum of a bunch of things from some quadratic function. That could instead be thought of as adding up like the differences of cubes. So this is 6 cubed minus 5 cubed, etc. And what we end up with is like 6 cubed, right? Who's with me? Okay, so the takeaway from this whole conversation is that if you want to know what the sum of the squares is, perhaps what you should do is take the differences of cubes and then set them all up to add so that they telescope. Who's with me? Okay, good. Spin the camera. We're going to go over here. All right, so that's exactly what we're going to do now. And if you kind of didn't understand that, it kind of doesn't matter that much. So all right, back over here, what I want right now is a formula for a cubed minus a minus 1 cubed. All right, go. You might like just know that by heart or something, but for those of you who don't, take a minute and give me that answer. I just know this by heart because I'm a math teacher. All right, I got 3a squared minus 3a plus 1. Agree? All right, so as promised, if you take the difference between a cube and the previous cube, what you get is like a quadratic expression. Okay, and now I'm going to do the exact thing that I said I was going to do. I'm going to add up the differences of cubes. Okay, let's go. So we're going to write an equation: n cubed minus n minus 1 cubed. All right, well, what is that? According to our happy formula that we just figured out, this is going to be 3n squared minus 3n plus 1, yeah? Okay, write kind of big, because we're going to write kind of big. 3n plus 1. Okay, now, directly underneath it, exactly like we did over there, but sort of in general, I will now consider n minus 1 cubed minus n minus 2 cubed. Well, what is n minus 1 cubed minus n minus 2 cubed? It's still the difference of two successive cubes. So I can still use this formula, but now the a is like n minus 1. Yeah. So then this is going to be 3 n minus 1 squared minus 3 n minus 1 plus 1. All right, everyone get it? Ask now. If you have a question, ask now. 5, 4, 3, 2. Okay, don't stop. More. Do another line. N minus 2 cubed minus n minus 1 cubed. Wait, oops. 3, I mean. Okay, and well, that's also a difference of successive cubes. So what do we get?
3 minus n minus 2 cubed.
3 n minus 2 cubed. Right now, a is just like n minus 2, yeah?
Yeah.
Minus 3 n minus 2 plus 1. Okay, and let's skip down to like, I don't know, like most of the way down or whatever, till we get to, it's gonna keep going down, 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 down. So let's do when A is 2. When A is 2, what do we get? 2 cubed minus 1 cubed, yeah, don't simplify, is
Equals
3 times 0.
Minus.
oh, yeah, no, it's not 0, it's
3 times 2.
3 times 2.
right now it's 2 cubed minus 1 cubed is according to the formula. It's just A is just 2 now, right?
Yeah.
So it's like 3, 2 cubed minus 3.
It's
2
2 squared.
2 squared.
Oh crap.
Yeah.
Like making mistakes everywhere. Alright, and then this is 2 plus 1, agree? Okay, and does that like check out number wise? That's really good tell us, right? Because 8 minus 1 should be 7, is that 7?
Yeah.
12 minus 1, yeah, good. Okay, and then the last line is 1 cubed minus 0 cubed equals 3. Now A is just 1. So 1 squared minus 3 times 1 plus 1. Okay, so all I did was to write n equations, all of which are true, because they're all just the pattern that we found over there. And now, of course, what am I going to do with these n equations? Add them, yeah, good, exactly. And on the left-hand side, the awesomest thing happens, which we've kind of already come to expect, which is that it's going to telescope, right? Because n cubed, you're subtracting n minus 1 cubed, but then you're adding n minus 1 cubed. And you're subtracting n minus 2 cubed, and you're adding n minus 2 cubed. What do you get on the entire left side? N cubed. Okay? And now, this is the cool part. Let's add like a column at a time. What happens if you add 3 times 1 squared plus 3 times 2 squared plus 3 times 3 squared plus 3 times all the way up to 3 times n squared?
You get 3 times.
You get 3
N
times the thing that I set out to discover, right?
Yeah.
The whole goal of this lesson is to figure out what 1 plus 4 plus 9 plus n squared is, right? Well, that's what this is. This is 3 times the sum from I equals 1 to n of I squared. Because it's 1 squared plus 2 squared plus n squared. Cool, cool? Okay. Well, now let's look at the next column. This is, I'm subtracting 3 times 1, then I'm subtracting 3 times 2, then I'm subtracting 3 times 3, all the way up to minus 3 times n. So what's that? It's this, wait, stop saying triangular numbers. It's 1 plus 2 plus all the way up to n, but all of that
Times 3.
times 3, and we're subtracting. Good. So minus 3. Okay, and finally, I'm adding 1 how many times? N times. So total is n. Whoa.
Whoa.
Whoa. So now I have an equation, and one part of this equation is the thing that I want. But fortunately, someone say something mildly observant. What is the sum from I equals 1 to n of the i's? It's like known. Yeah, good. Yeah, she's just like, dude, we already know that formula, right? All right, go. Using, from this point, it's just algebra 1. Solve for the thing in red. Guys get it? did it right. Oh, no, I didn't. You're right. Sorry. Should be minus that, right? And get like a common denominator and like make it pretty and stuff. All right, I think you get something kind of nice, right? Ish. Let's see, does that factor? Yeah. And both 1, 2, whoa. Oh, we're going too fast.
Yeah, maybe.
All right. So this is like pretty cool. Did you guys get what I got?
Yeah.
You gotta just do a bunch of algebra, like do a quick, did that work out? Yeah, and then just like factor and stuff, it makes it pretty. Okay, so, oh, I wrote the wrong thing in the box. This is the sum of the squares. All right, so like success. And do you feel that this is kind of like recursive, right? What if I wanted to know the sum of the cubes?
N times n plus 1 times 2n plus 1 times 3n plus 1.
Oh no, she's just guessing that
Yes,
the
I
formula
guess.
is what she wants it to be, and she's wrong.
I'm worth a try.
But no, what I meant by recursive is that the procedure is recursive. If this was my goal, how would I go about